Grać. Let us start our seminar today. The speaker Takashi Takebe, he will say about dispersionless hierarchies and which equation, sorry, dispersionless integrable hierarchies
and
Loewner type equations. Okay, let us start our seminar.
thank you for giving me such an opportunity. And today I cannot speak loud, sorry. So, hello. Okay. This person, I first explain what are dispersionless integrable hierarchies, and then I will show how they are related to Loewner type equations, which arise in the theory of conformal mappings. Okay, dispersionless integral hierarchies is a sort of classical limit of integrable hierarchies like KP hierarchies, Toda lattice hierarchies, and so on. Well, MKP, PKP, and so on. Yeah, probably I shall talk only about KP hierarchies, but there are many variants of what I'm going to talk about. And these dispersionless hierarchies were found in 1990s in this context, and actually they were found in the theory of, for example, string theory or topological string theory or whatever it is, and as their genus zero part of the partition function of those physical systems. And it was the story in 1990s in the last century, but in this century it was found that such dispersionless hierarchies are related to theory of conformal mappings. So you know Riemann mappings theorem, and it is this theory is related to such a Riemann mappings theorem. And there are several variants of that story. And well, for example, Toda lattice hierarchy is related to so-called Laplacian growth theorem. And about which probably you'd better ask everybody, which Professor Newman. Today I'm going to talk about Loewner type equations, about which I shall talk about later. Well, probably you have heard about SLE, Schramm-Loewner equations, and it is actually related to this part, not stochastic part. Okay, so I'm going to review briefly about the theory of KP hierarchy. Well, there are several equivalent formulations, but for me, the lax representation is most convenient. The fundamental ingredient of this system of equations, partial differential equations, is that this so-called lax operator, where T is set of infinite number of variables, and U2, U3 are functions, unknown functions. And here, D is a partial differential operator, and X is, today in today's talk, we can identify X with T1. So let me identify this first variable and X. So this is it. And what are they? Well, maybe some of you might be scared, or some of you know this very well. But anyway, they are just algebraic inverse. I mean, well, this is a usual Leibniz rule, and so this defines the commutation relation of this object, generator of algebra or whatever, and function, another ingredient of this algebra. So from this, we can so this. Yes. So, well, details are not necessary, so they can just skip that. We can write down computation relation. It becomes infinite series, but still there is certain reasonable computation relation of inverse and function. And so Lax representation of the KP hierarchy is such equation where this is usual commutator, and L is that L, and Bn is essentially nth power of this L with positive part, which means if you have certain series of differential operators, pseudo differential operator, then positive part, non-negative part is just such a differential operator. Actually, this, oh, yes. Yeah. Sorry. But yes, different differential operator part. So in general, we have such a tail of negative of the operators, but we just ignore to get Bn from this power. So yeah. Well, maybe we need another symbol. If I put negative, then it means the part which we threw out in this definition. Again, this equation with commutator is called Lux type equation, and of course, this is equivalent to this expression. Yeah. Then actually, this is actually compatibility. Oh, sorry. And so this is a system of equations. And this is a part of compatibility condition of such linear system of partial differential equations. So this acts to a function as a differential operator. And because we defined Bn, this operator, from A like this, the whole compatibility conditions for this linear system can be recovered from this KT hierarchy. And we need a special kind of solutions of this linear system. We can show that KP hierarchy has such a solution of this linear system of such form, which is called Baker hierarchical function. And a very important ingredient of the theory of this hierarchy is so-called tau function. Uh, uh, can express this Gaussian function in this way. Is a function of T1, T2, and so on. And we shift the variable by certain amount. Where this symbol is standard notation for such object. And maybe you have heard about so-called Hirota bilinear equations. Functions. This is equivalent to the KP hierarchy there. And in terms of tau function, this is so. So this is a residue symbol. So integration doesn't have any serious meaning. We just take the coefficient of set inverse in this expression. Where, you see, this can be expanded as a series of in Z inverse, and here we have some large series of Z. So by multiplying them, we have some series, and take the coefficient of Z inverse, then it should be zero. That is, we can show that it is equivalent to the KP hierarchy. Yes. Maybe I spent too much time for the review. Well, dispersionless, yeah, let me in this way, for short transportation, dispersionless KP hierarchy is formulated in this way. Here, well, to distinguish that they are, let me write it in this way. And yeah, here we have certain operator, but replace operator of the differential operator with certain variable tab. Then, yeah, KP was defined like this. So we define B operator corresponding to Bn as Ln positive, but probably the meaning is already clear for you. Take just polynomial part of the product. And so we know what is this, but committed is trivial because they are just from a series. So instead of committed, we take Poisson bracket, which is defined as usual. This is called dispersionless KP hierarchy, and why it is called dispersionless. Where is dispersion? Actually, yeah. KP hierarchy. If we add some additional constraint for L operator, which requires that square of that image series, so the differential operator with negative of part should be just a second order differential operator. Then it becomes so-called KTV hierarchy. And one of the equations in that hierarchy can be interpreted as this KTV equation, which probably you know very well. Here, X is one, and yeah, in the ordinary theory of KTV equation, T is time. But, in this context, T is T3. Correspondingly, let us require that the square of this L, that L, is just a polynomial. Then, in the same procedure as like this, we have such an equation without this term, which comes from dispersion. So this is called dispersionless KDE equation, and therefore we call such a hierarchy dispersionless KP hierarchy. Although dispersion in this theory does not play much role. And actually, we can construct a similar theory like KP hierarchy. But well, yeah, maybe I'd better skip. And well, so we have KP hierarchy and dispersionless KP hierarchy, and we replaced the operator by some symbol. But actually, yeah, better interpretation of the relation of these two systems is like this. Let's consider an intermediate object, which we call H bar KP hierarchy. And the ingredient is L operator. L operator of the KP hierarchy. Something like this. And the L operator of this H bar KP hierarchy is often like this. And coefficients, namely unknown functions, are also dependent on this auxiliary parameter. But important requirement for these functions is that these functions or auxiliary formal power series are Taylor series in this parameter. Does not include inverse powers. Well, L includes inverse powers by H, but they come only from this part. Then probably you have already expected, but HVAC hierarchy is defined by these Lux type equations, where Dn is defined just as before. And as you see, if we put or substitute 1 to h, so if h bar goes to 1, then it recovers the KP hierarchy. Or if h bar goes to 0, then we can recover dispersionless KP hierarchy as the leading order of these equations. Well, so well, order of this operator is m, but we define order of such operator as m minus n. Then actually, since this starts from the, this contains only non-negative powers of m, or these operators, and this operator is order 0. And so if we expand this equation by order defined by this section, then the zeroth order part of this equation is the dispersionless KPI. So in a sense, this is a principal part of this. Yes. Yeah. Yeah. Well, just rescaling the T1x, now we do not have such a form of say. Yeah. Yes. Well, essentially, yeah. Not much. Yeah, actually, yeah. Yes, probably. Yeah. We have to rescale Tn to h but Tn and so on. And for example, this goes to h bar 13% and so on. Yeah. So anyway, yeah. Yeah, from KP hierarchy, yeah, this operation is not very good operation. Actually, yeah, to see how the structure, for example, symmetry, etc., of this KP hierarchy are inherited through this. Yeah, we'd better use such a operation. And yeah, idea is probably as you said, just divide X by S. And but however, for example, tau function is dependent on H bar, and actually it yeah. We can show that we can choose the function of with such behavior. And yeah, actually F0 here determines everything in the dispersionless KP hierarchy. So this is the leading term of the tau function in a sense. So that it is reasonable that such a leading term determines the leading term of the KP hierarchy. And so this is often called logarithm of tau function of the dispersionless KP hierarchy. And well, I said that the dispersionless KP hierarchy was introduced, was found in 90s as the from in the context of string theory or whatever. Actually, yeah, please do not ask details of string theory. I'm not a specialist. Well, in such theories, there is a so-called genus expansion of the attention function, which is some important ingredient of those physics theory. And so from the modular space of the genus G or whatever, such a coefficient Fg is determined. And this is this has exactly this one. And F0, the genus zero part of such it gives the dispersion that's a solution of dispersion KPR. That relation found in 90s. Oh, yeah. Well, let me gradually move to the relation with complex analysis, Loewner equation. And yeah, this is probably the cut. Yeah, let's consider a certain class of solutions of dispersionless KPR. it is an equation for such series, and T is infinitely many variables. Infinitely many is too many. So let's find such type of solutions where this is a two variable function. This is one variable, and this is another variable, which is this parameter. And let's find a two variable function f and some function, one dimensional, of these infinitely many variables. And let's find a solution of dispersionless KP of this type. Such a solution can be characterized as follows. Okay. If this is a solution of dispersion hierarchy, then this is a certain, this is the inverse function of a solution of certain ordinary differential function equation. Let's call this as T lambda Z. Well, here the meaning of the inverse function is with respect to this second part. And let me write. Toda equation is such an equation. here, this is a function of lambda, which parameterize as parameterization of this solution number. So additional function, which is called a driving function. A1 here is the first. So this is not non-trivial. Non-trivial question. But this numerator is A1 is well, this is some external function, yes, some function. And the converse statement is also true. Namely, if G is a solution of Loewner, and F is the inverse in this sense. And sorry, not yet. And lambda, we need to specify lambda. Lambda is a solution of such a series of case linear differential equations. Here, phi of n depends on lambda and lambda w, and actually it is essentially power of f. And let's take the again, let's take the positive part. So in the context of KP, this is almost Bn. Yes. Yeah, yes. And so if f is the inverse function of the solution, Loewner equation, and lambda t is a solution of this system, then we can obtain a solution of the dispersionless KP hierarchy. And so I said that Loewner equation is related to complex analysis, conformal mappings. Actually, it was found in the early 20th century, I guess, by Loewner in the theory when he tried to prove the Bieberbach conjecture. And what is it? Well, yeah, as we know, any simply connected domain, except for the complex plane, in the complex plane are homomorphically equivalent. And for example, if we pull out certain curve from the upper half plane, it is equivalent to upper half plane. And well, let's take some long curve, but just truncated at some point. And let's normalize this conformal mapping in that way, namely in this way. Then such a conformal mapping is unique by Riemann mapping theory. Well, yeah. Usually we have scaling freedom, and we can move parallelly, but everything is fixed in this. Then such a mapping function is a solution of this Kodan-Loewner equation. That's theory of by Loewner. Karl Loewner. Well, that's of dispersionless KP hierarchy and the theory of conformal mapping. Well, at this stage, maybe you think you can think that is nothing more than a well, this case is related to GL type symmetry. Is orthogonal type symmetry, and we can take dispersionless limit, and from this, by the same procedure, we can deduce Loewner type equation of this type, namely quadrant Loewner equation is differential equation for the conformal mapping between quadrant and quadrant minus. Well, and there are many other examples from so-called DKP. We have dispersionless DKP, and from this we have a Komatsu equation. In this case, it is already out of the realm of the Riemann mapping. This is equation for the conformal mapping of animal. And yeah, there are another so-called constrained Toda, which was found by Dispersion. We have symmetric radial Loewner equation. In this case, we pull out two curves symmetrically from plane minus. Yes. Oh. Well, if it is rated in that way, that is very interesting. But at least up to now, we do not know why they are rated. I mean, yeah, we know proofs of these relations, but that's just proof, namely, just relatives. Yeah, yeah, but how, why? Yeah, well, yeah, if that's the, yeah, if that's true, then I'm very happy. Yeah. So that's it. Thank you. Questions?
Okay, thank you. Any comments? Any questions?
Yes. Yeah. You mean something like this? Then everything is yeah, the same. We flew out this part too. Yeah. I don't know. Yeah. For all the solution of these questions, you mean, right? Solution of this Toda equation or Toda equation or solution of dispersionless PPR. which so we don't know. So yeah, by writing the equations, we can show that they are related. But for each concrete explicit examples of conformal mapping like this, what happens? I don't know. Yeah, topology changes, but still, Loewner equation is valid. Or just ignore this part, or just
remove this
and
area.
remaining simply connected. Yeah, just one comment. No, not. I don't know whether it is related to this, but for SLE, we replace this lambda by Brownian motion. Time some parameter.
And if you consider the stochastic Loewner equation, can you transfer the integration measure to integration over couplings?
Part is of course valid, but what means that stochastic Brownian motion to this integrable hierarchy? I don't know. I want to know, but still I'm not sure.
Thanks.
Any other comments, questions? Maybe by Zoom? One more.
Well, that was his question. Yeah. The answer is yes. I don't know. I want to know, but I don't know.
We don't know. Okay. Let us thank our speaker again. Okay. Thank you very much. So